Thank you very much. It's a big, big pleasure for me to be here. Thank you. Thank you, organizers, for having me. I actually want to talk about broader things, like interpretable and trustworthy machine learning today. And I wouldn't be here talking about it if it wasn't for this black box algorithms. What are they? Well, in the context of machine learning, they are essentially models that take data as an input, and they spit out predictions as an output. But it's very difficult, if not impossible, for us to really understand what happens in those models. And it's difficult to understand the relationships between those data features and predictions. So this is typically the case in very complex machine learning algorithms like neural nets or ensemble models. And ironically, what makes those algorithms very accurate also makes them very difficult to interpret. So how do we evaluate those models? How do we build trust in them? So currently, the most common method is to evaluate them through various metrics of accuracy, whether it's a total accuracy, sensitivity, specificity, you name it. Is there anything wrong with this approach? Well, there is actually a lot. So the reason why we shouldn't rely solely on accuracy is because under so-called accuracy, there are a lot of things other than truth, or maybe other things than truth. So it could be that the model is picking up on noise rather than the genuine signal. It could be, the model could be confused by correlated features that we fed into it. And finally, our algorithm can be too specific to the data that we showed to it and doesn't generalize well. And the following example will explain very well what I mean by that. So imagine you're a data scientist building an algorithm distinguishing between the pictures of huskies and wolves. And so far, you've done a really good job. So you've classified correctly, what, over 83% of your pictures, and you just made one mistake where you took a husky for a wolf. So hands up, who thinks this is a good model? You know what, I always get it. I never get people who think, yeah, this is a great model. So, OK, I understand that you may be skeptical, but how would you justify your skepticism? But just by looking at this, right? Accuracy. So what if you had access to model inner workings, models' interpretation of the data? So here, on the left-hand side, you have the original picture. And on the right-hand side, you see only those features that were key in generating the prediction. So you see, in terms of huskies, the model picked on the different body parts, like a torso, paws, a snout. So you think this is a reasonable behavior. So I trust that. But when you look at the wolf, all it picked on was the background. And in this case, that was snow. So what you actually built was an excellent snow detector. So what is there about simple models? What makes them so easy to interpret? And is there something about them that we can use in black box algorithms? So let's say, again, you're a data scientist working in the healthcare industry. You want to build a model classifying cancerous cells, or distinguishing between healthy and cancer cells. And if you find it difficult to relate to this question, it's any classification problem. So whether it's a question whether the loan will default, the prisoner will commit a crime, whether the machine is going to break, doesn't matter. So we start with one observation, and this is absolutely useless. We have two features, cell shape, cell size. We know nothing about this observation, really. But if we take historical data, and we have many examples of cells with a wide range of cell shapes and sizes, we can try to identify in this case, linear function that will distinguish between the two labels. And in this case, because the relationship is linear, we can really easily create rules helping us interpret the relationship between features and the outcome. So, OK, not every relationship in our life is linear. What about non-linear relationships? Well, we can use decision trees. They are really good at spotting non-linear relationships in features. So again, we have cell shape, cell size. We can very easily create a decision tree that will give us rules for distinguishing between the two labels. And that's also very easily interpretable. So now the problem starts with big data. And it's not only because we feed more and more features in our models, making those relationships more complex, but also the actual relationships between those features and the outcome become more difficult to interpret. So you can imagine if here is the one feature, let's say cell shape, the other one is cell size, and the colors indicate the class, there's no way you will build an easily interpretable function that will encompass all that complexity. So we're not completely blind, right? We have some tools and methods to tell us what our even black box algorithms are doing. So let's say we have random forest, which is like a very typical ensemble model consisting on hundreds of decision trees. We can, let's say, get the feature importance plots to understand better which features were most critical in producing the prediction. And then we can look at the partial dependence plots and actually understand the relationship between the marginal effect of what that feature has on the outcome. And even we can see that even if it's nonlinear. The problem with those tools are twofold, at least. So one is that not all of those tools are available for every algorithm. So for instance, there are no partial dependence plots available for neural nets. And the other one is that they usually give us an idea of the global model. So it's very difficult to use them in order to understand why, in this particular case, in this particular observation, the prediction was like this rather than like that. So one solution to this problem is LIME. LIME stands for Local, Interpretable, Model-Agnostic Explanations. And it's a quite new tool. So the first publication on LIME was published, I think, August 2016. And despite being so new, it's already available in Python and R. So LIME is really a framework to understand any or interpret any model, including black box model. And not only models we have now, or algorithms we have now, but also those that we will develop in the future. And let me explain why. One thing is that, yeah, it's local and it's model agnostic. Local means that we don't care about the global model. What we care about is about single observation or a cluster of very similar observations. So we analyze them at the level where we can apply those simple models that I just mentioned to you. So in this case, we could apply a linear model to distinguish between these two groups of observations. Model agnostic means that for LIME to work, it basically only needs the data that was fed into the model and the actual predictions. So we don't care what model generated those predictions. We just care about what those predictions were. That's why we can use LIME for models we know today and also those that we'll have in the future. Under the hood of LIME, there's lots going on. I don't want to bore you to death at the moment, but in essence, what it does, it's for every single observation, it generates multiple data sets. So I think by default, it's about 2,000 data sets that are perturbed. So they're never the actual data set that we fed into the model. They differ. But then it calculates the the distance between those new data sets and the original data sets, so we know how similar they are. And then also it makes predictions using the algorithm on those data sets, those new data sets. Then finally, it picks number of features that explain that model best. And then basically, it just fits simple models to those observations and creates a coefficient, which is essentially the similarity measure that we created in the beginning. So I listened to the interview of people who designed Lime, and they said, oh, it's a really simple tool. It's a really simple tool. Well, it's some stuff to get your head around, but in essence, when you think about it, it's actually not that hard to understand. But anyway, so let's carry on with interpretable explanations. So we still are data scientists working in healthcare. We're still trying to distinguish between healthy and cancerous cells. So imagine you have a data set where you really have a class where the cell was benign or healthy or was cancerous, malignant, and you have all sorts of features describing those cells. So what would Lime do? Let's say you have a model, neural nets, that is highly accurate, 95%, let's say. And now you have to talk to the doctor, oncologist, and convince him or her that this is a great model and they should use it. How would you convince them? Well, for the start, you can show them what makes model be correct. So you look at the correctly predicted classes. And let's see here, these are correctly predicted healthy cells. And you can see that you have a number of feature importance plots separate for each observation. And what they list is like which observation this is, what was the actual prediction, what is the label, and also how confident the model is in its prediction. And obviously, you have here listed features were most critical in producing that prediction. And also, green color indicates that that feature supports the prediction, and the red one, that it contradicts the prediction. So again, going back to healthy cells, you can see that for those, in most cases, the cell size was small, the cell shape was regular. So yeah, the kind of things that even we laymen understand that would be typical for a healthy cell. So far, so good. But what about correctly classified cancerous cells? So we have a row here, and you can see that in all those cases, the cell shape and cell size values were high, meaning that they were big and they were irregular. OK, so this is pretty good, but your oncologist is still not convinced. He or she wants to understand where the model made mistakes. So we can look at incorrectly predicted observations. And here, the prediction was that it's a healthy cell where it was not. So what made model think it's a healthy cell? Well, cell size was small. And in here, also, the shape was regular. But there were other things that also contributed to thinking that it's a cancerous cell. So even though the model made mistakes, those mistakes were made for the right reason, if you know what I mean. So those cells had features that were typical also for healthy cells. So those kind of things would actually increase your trust in the model. And without having those interpretable explanations at hand, would be impossible to make your case. Now, why is it important? It's important for two types of reasons. So one is technical type and non-technical type. Speaking of technically, why it's important? It's important because of trust. So by understanding what features our model picks on, we can judge whether it behaves reasonably or not, and therefore whether we can trust it or not, just like with huskies and wolves. It's important because of prediction. So we also want to understand how the model works, and we want to understand how it's going to behave when it's applied to new unseen data. If we understand what features it picks on, we ourselves can better understand how the model will behave. And finally, it's important for improving our models. So obviously, if we understand what are the biases in our sample, in our data, again, like with wolves and huskies, we can either modify our samples or data in a way that will improve model performance. So that's the technical side. What about non-technical side? Well, there's a legal side to it. So obviously, we're only a month away of GDPR kicking off, which means that basically every company that does automated algorithmic decision about the customers will have to comply with so-called right to explanation. So that means that the customer will be able to demand specific local explanations for why his or her application was declined or why he or she was priced in a certain way. So this is obviously the legal side. But from the social impact point of view, it's absolutely critical that our models don't pick even on genuine signals that may put vulnerable people at disadvantage. So Zeynep Tufekci, I believe that's how you pronounce her name, gave excellent example in her TED Talk, where she said, imagine you're trying to target people for marketing campaign to buy a trip to Vegas. In the past, you would have very clear rules what people you target. You would target people with of a certain financial profile, or maybe young people who like gambling. It would be very clear who you're targeting. But if your model is opaque and unclear, perhaps it would be able to identify people who are bipolar just at the offset of their manic phase, making them more prone to gambling and overspending. The thing is, you wouldn't even know that. That's why having access to those interpretable explanations is absolutely critical. Then finally, think about scale with anything you do. So data scientist Kasia O'Neill, in her book, talked about weapons of math distractions, or WMDs. These are the algorithms that share three properties. They are opaque, they work at scale, and are damaging. So they're opaque, meaning they're either proprietary or they're black box. Therefore, we don't really understand what's going on with them. They work at scale, means they don't just affect your department or your company, they affect populations. And finally, damage. Damage usually directed unintentionally at people who are vulnerable and already at disadvantage. So one of the excellent examples she gave of WMDs is Compass. Compass is an algorithm giving you an idea of risk of recidivism, and it's used in many states in the US. And the idea behind using Compass was to remove human bias and take a wider context, data context, into consideration, which is noble. But what happens was that there were concerns that the algorithm itself is biased against black men. So it puts them at higher risk of recidivism, higher than in reality. There was a huge discussion on the internet whether that's true or not, and it all boils down to definition, statistical definition of fairness. So depending what tools you use, the algorithm will be judged as biased or not. But even if it's not, that doesn't mean that everything is OK with it. So among other things, it relies on questionnaires that ask questions that are completely out of prisoners' control, like whether they were brought up in a household by a single mom, or whether their friends or neighbors committed a crime in the past X months. So one take-home message from that is powerful algorithms can be harmful in fact, even from the technical point of view, they're not biased. But that's not the worst thing. The worst thing is here, published just in January this year, where it turns out that, well, two things really. So Compass's total accuracy at the moment is about 65%, which is appalling, if you ask me. But that also means that that accuracy is as good as anyone's guess, yours or mine. Given the data, we could give our guess and be as accurate as Compass. That's one thing. Not only that, Compass, in a current form, takes 137 features into account. But you can reach similar accuracy by running a very simple linear model that takes only 2 features into account, age and number of committed crimes in the past. That's it. None of that bias, none of that fuss, not all this money spent is necessary to achieve just that. So Lime obviously links all those cases, but it's only the beginning, or it's only part of my vision of the future that I share with Joe Buolamini about the future of algorithmic justice. So to create that vision, we need at least 3 things. So one is we need to identify bias, and whether we use Lime for that, or whether we use software audition, or we collect someone's experiences, doesn't matter. We need to be able to identify that bias. Finally, well, next one is we have to curate inclusivity. And by that, I mean including people of various backgrounds in data science by incorporating more various perspectives. But also, more technically, we need to curate inclusivity by including more representable training sets. And last but not least, we need to think about social consequences of our models. So we feel safe when we develop our models at our desks, at our laptops, and we think they're going to stay there. But when you do that, think, what if your model takes over the world tomorrow? What will be the impact? So my last slide. These are my 2 kids. And when I think about the world of the future, I think about them. And I think about the world they will live in. And I want that world to be the world that doesn't propagate existing biases and discriminations, the world that will not prey on vulnerable people. So, and this is the world that is not up to just politicians and policymakers. It's up to us geeks. We're a huge part of it. So think about it. Thank you very much.
Okay, we have time for some questions.
Are you using something like Lime to deep learn?
Yep. So we're still trying to scale it up to the point where we can use it for pretty much every process we run. But we already run it in cases where we see a weird behavior of our models, and we want to understand why that happens.
And that ties in with the regulators' acceptance for it if you're using deep learning and things.
So I don't think at the moment it's specifically required by GDPR people. There are lots of other processes that are, and we're working on them. But our idea is that we want to be able to store our predictions and its explanations in a table, so that at any point, if anyone comes to us and asks why did you make a decision on me 2 years ago, we should be able to go back and understand what algorithm version we ran at the time, what predictions that was, and why it was. Is someone there?
Are you only using Lime, or are you also using other techniques?
Oh, absolutely, yeah. You use a whole range of techniques. But Lime obviously is very useful in cases where some of those techniques are not available. Or as I said, we have very specific questions about certain observations.
Can I ask what other techniques are you guys using?
Yeah, but it really depends on the use case. So So let's say we're running a gradient boosted tree, and we want to just understand, like I gave an example of feature importance plots and partial dependence plots. That will already give you an idea of what's going on. But as I said, sometimes it's difficult. So obviously you look at single features and the relationship between that feature and the outcome. But often there are underlying complexities like interactions between other features and so on. So it's not always easy, but yeah, obviously as a data science community, we have good tools that usually are enough, but not always. Sorry, who's?
So maybe it's just my limited understanding of it, but doesn't it, can you really make a statement of like a reliable explanation of why a certain decision was made if you're not looking at all at the model? So you sort of drop the black box and put something on top of it, and it tells you, oh, this was flagged wrongly because something like that. Doesn't it sort of defeat the purpose if you're dropping the whole model?
I'm not sure. So I'm not sure if
I'm... made a decision for a completely different reason because
yeah. So yeah, obviously you can. There's always a risk that applying those simple models may be misleading, that the actual reason was different. But given what Lime does under the hood, so it's almost like you imagine running a random forest, right, by creating permutations of your data, and this way giving different examples for the model to learn. And then also understanding how similar this was to the actual data set. And then also working locally where you can actually draw very simple conclusions on a very small sample of data. And you do that at, well, I don't want to say at scale, but you do that at minimum for 2,000 times. I think that's a pretty good approximation of what could be happening in the actual black box model. But obviously, there's no 100% guarantee that that's exactly what happened.
Is the line framework or whatever, is it restricted to supervised task, or is it a general framework that you can apply to unsupervised tasks as well?
Yeah. So the question was whether Lime is restricted to just supervised learning or other techniques as well. So at the moment, it's restricted to classification problems. I don't think you can apply to regressions. Regression problems. But at the same time, you can apply to text analytics and image recognition models. So there's still some work going on so that to cover all, again, supervised spectrum, but obviously you wouldn't be able to apply it to, I don't know, some kind of clustering algorithms. Yeah.
Are there any other questions?
There's one more here.
How did your work in evolutionary biology affect what you do now, or was it not?
Totally, God. No, I spent a lot of time during my PhD coding and doing stats. Yeah. I think the biggest difference between like data science in the industry and back in academia and biology is that essentially what we do in academia is inferential statistics. So we're really trying to understand what happened.
I was more asking rather than the actual tools or the
tools.
mechanics in terms of the understanding of the way people behave.
So in terms of tools, obviously I spend a lot of time coding. So my tool of choice is R. But obviously we used Python and we used lots of other pieces of software that's not necessarily code-oriented, if you will. But in terms of data sets, I would think we really struggled with sample sizes and so on. But other than that, the data was representative in a sense that was as messy as you would expect in real life. So
I was really trying to ask was, as far as I understand from evolutionary biology, you have an understanding of the way that people behave. You're now working in an insurance company. Do you see some of the same aspects that affect the way that you see that or not?
Well, I would think when you work in evolutionary biology, you work on a very tiny piece of it, and mine was disease. So it wasn't so much of the behavior, although you obviously have tools and theory to understand it. At the moment, I'm not very much involved with, let's say, marketing data, so it's difficult to apply directly. But definitely, well, I suppose this is not just data question. It's a question of your perspective, how you look at everything that surrounds you by thinking about evolutionary approach. So yeah, obviously it is life-changing.
Continue what you say just now about the inferential stats in the academia and
Oh, sorry. So the question is about inferential statistics versus predictive analytics. So yeah, again, the change in perspective is huge. So essentially in academia, we almost want to overfit our models. We actually want to really understand what happened in this particular time frame, in this particular case. And I still remember my supervisor's words who said, don't care about those people who try to build fancy predictive models, because we don't care about that. That's exactly what she said to me. So obviously the perspective is completely different. And we try to generalize as well as we can in predictive analytics. But at the same time, we don't care so much about the drivers of phenomena we're looking at. We just care about prediction accuracy, really. So yeah, it's a huge shift, philosophical shift, I would say. Yeah.
Lime has linear regression.
Sorry?
Lime has linear regression.
Yeah. So Lime has linear regression, but it can't be really, at the moment, at this point of development, or last time I checked, it's not applicable to regression problems. So when you model amounts rather than classes, if you know what I mean. But actually, Lime has both, has decision trees and linear regression that they use it under the hood. Oh, hello.
I've got a question about where your decisions are looking. So I think it's really interesting to think of data science being two parts. One is the prediction, one is then going and explaining that.
Yeah.
Did this come about because you were asked to do it, or is it something that you thought is going to become more important when you think about it?
What you mean Lime?
Yeah, the idea of interpreting results.
No. So to be perfectly honest with you, I got interested in Lime because it was like a hot topic on Twitter, and then I wrote a blog about it. So, but obviously, when you start thinking about it, it has huge consequences. So no, that was the reason. Yeah. I think.
Any other questions? Okay.
All right. Thank you.
Okay. Let's give a big hand to Kasia. Thank you very much.